Hello everyone. Today in this problem we're trying to analyze a frequency selective circuit, or in other words a filter. I'm going to actually analyze the circuit in general terms. In other words, I'm not going to use the values that are given here to begin with, and then once we develop all the equations, we can then replace the values in the equations that are developed. And that's more general, and it happens to be actually a slightly more convenient too, since these numbers are relatively small, and working with these very small numbers is not while you're trying to develop the equation is not convenient. Okay, so let's start the discussion. So like always, we're going to label the circuit. So this is one node, that's another node, and that's another node. Then we label the currents. Now once we assume that this is ground, then this immediately becomes VI, and I'm going to write capital I and capital V, indicating that these values are now immediately are in Laplace domain, because I'm going to write all the equations directly in the Laplace domain. And then these are the currents. I'm going to call this IL, I'm going to call that IC, and call this IR. So there's one KCL in this circuit, and we're going to write it. Let's just switch to black. So and there is actually this. So there's actually current going into this node, but we are not interested in that current. But for the sake of completeness, there's actually a source here. So whenever there's a VI, that means that there's a signal source there, and therefore there's actually a current I here too. You can write a KCL equation for that node that says II is equal to IL plus IC, but that's really not necessary, because the reason is that we are actually looking for a ratio between output to input as opposed to absolute values, and therefore one of these equations is not important. In other words, we assume VI is already known. Okay, so that said, KCL, I'm going to write both, but we don't really need to. So II is equal to IL plus IC, and then IL plus IC is equal to IR. Now we start writing equations for components. There are three components for the inductor. The equation is IL is equal to VI minus V out over LS. Like I said, I'm going to use L as opposed to the value given. And for the capacitor, IC is equal to CS times VI minus V out. It's the same as saying VI minus V out over 1 over CS, which is the impedance of the capacitor. Then finally for the resistor, IR is equal to V out over R. Now you start manipulating these equations with the goal of calculating V out over VI, and the result is going to be something like this. V out over VI in the S domain is basically I'm going to just use my knowledge of a voltage divider equation and write it in that form, but really you just manipulate these equations and you're going to get the same thing. So it would be R over R plus Ls, which is the impedance of the inductor, in parallel with 1 over Cs, which is the impedance of the capacitor. Now let's actually evaluate this. So this would be R over R plus. Now these two in parallel would give you Ls times 1 over Cs, which is L over C over Ls plus Cs, which would be 1 plus LCS2 over CS. Okay, so these two C's go away. You get LC over 1 plus LCS2. So generally now I can write V out over VI as R times 1 plus LCS2 over RLCS2 plus LS plus R. So that's the equation for the transfer function of this filter. Now I can rewrite the same equation to get rid of the factor that is multiplied by S2. I'm going to divide both top and the bottom by RLC, and that's going to give me this equation 1. It's going to give me S2 plus 1 over LC in the numerator, and in the denominator I'm going to get S2 plus 1 over RCS plus 1 over LC. So this equation is a lot more telling. Now, in order to understand what kind of a filter we have, we discussed this before, and we're going to have to try the two ends of the frequencies, like evaluate HS at by replacing S by J omega. So I'm going to evaluate H J omega at this point, which would be J omega to the power of 2 plus 1 over LC over J omega to the power of 2 plus J omega over RC plus 1 over LC. Now, if you notice, J omega to the power of 2 is J to the power of 2, which is minus 1, so that would be minus omega 2 plus 1 over LC over, this is directly minus omega 2 plus J over RC omega. Actually write it the other way around. It's plus 1 over LC minus omega over RCJ. So in the numerator you have a real number, whereas in the denominator you have the that's plus, sorry, you have a complex number. Now, to evaluate this, we are looking for the magnitude of both the hj omega to understand how much of the input signal is going to pass through. The amplitude of the output is basically the amplitude of the input multiplied by the magnitude of hj omega. So the magnitude of hj omega is the magnitude of the numerator, which is simply 1 over LC minus omega 2 over the magnitude of the denominator, which is the square root of the real part of that number to the power of 2 plus the imaginary part of that number, complex number, to the power of 2. So that would be omega over RC to the power of 2 plus 1 over LC minus omega 2 to the power of 2. Now if you set 0 in this equation, you can clearly see that obviously this goes away, that goes away, this goes away, and you end up getting 1. So H, I'm going to write that here. Actually, just it's easy to see. H, magnitude of Hj0 is basically 1. Now if you put omega equal to infinity, the order of this parentheses here, it's much larger than, it's basically order of this is 4, whereas the order of this one is 2. So you can ignore this term against that, and at that point again hj omega, when omega is approaching infinity, becomes 1 over LC minus omega 2 over 1 over LC minus omega 2. You're ignoring that against this term. And again, that's 1. In other words, at low frequencies, the magnitude of hj omega is 1. At high frequencies, the magnitude is 1 again. And in the middle, as you may imagine, this is going to go down and then come back up. So this is basically a band stop filter. So quickly showing kind of a, so if this is omega and this is the magnitude of hj omega, it starts at 1, it goes down somewhere in the middle and then goes back up. Now how far it goes down, well, if you look at this, you can actually clearly see that this is going to go down all the way to 0 when omega is equal to square root of 1 over LC. This term in the numerator is going to become 0, and therefore this down here is going to go all the way down to 0 if that's our 0. So I'm going to redo it. Starts from 1, go down to 0, then goes back up again to 1. So start from 1, goes down to 0, and then goes back up again. Now the frequency at which this is going to happen, we already said that it's square root of 1 over LC, the angular frequency. This is actually what's called the resonance frequency of this circuit. So if you're asked to calculate that, is basically for this specific circuit is the frequency at which the minimum happens. Sometimes for the other filters it's the frequency at which the maximum is going to happen. But in both cases, when you have a circuit including an inductor and a capacitor and a resistor, the resonance frequency is going to end up being the same equation. So omega resonance is equal to square root of 1 over LC, which is also telling you that the F resonance, the frequency of resonance, is equal to 1 over 2 pi over LC. This is sometimes also called the center frequency of the filter. Now beyond that, the cutoff frequencies that as we discussed is basically calculated based on this equation, that we are looking for a point where the magnitude of hj omega c basically becomes the maximum magnitude over square root of 2. In other words, in this specific equation, I'm looking for a point where hj omega's magnitude of hj omega c becomes 1 over square root of 2, because 1 is the maximum. We already established that. Now you put that in this equation and do the calculation, and you're going to get the values. Okay, now to actually calculate the cutoff frequencies. First of all, there are going to be 2 of them, but to calculate them, we have to solve this equation. Now I'm going to divide both the numerator and the denominator by 1 over LC minus omega 2. So this side of the equation is equal to 1 divided by square root of 1, because you take this and divide it by the denominator, you get 1 plus omega over RC over 1 over LC minus omega 2, the whole thing to the power of 2. And this, we're looking for the points where this is equal to 1 over square root of 2, which means now this term has to be equal to 1. So this is all, by the way, omega c. Let me actually rewrite this. So omega c cutoff frequency divided by RC over 1 over LC minus omega c to the power of 2, this whole thing to the power of 2 has to be equal to 1 over square root of 2, which then means that omega c over RC divided by 1 over LC minus omega c to the power of 2, the whole thing to the power of 2, has to be equal to 1. So now you solve this equation, you're going to actually get 4 different, this is a 4th order equation, so you're going to get 4 different frequencies. 2 of them are going to end up being negative, so those are not acceptable, and the other 2 are going to be acceptable, which then you just choose those 2 as your 2 cutoff frequencies, and those 2 are going to be in this form. I'm going to just write the result of that here. So omega c1 and 2 are going to be in this form, minus square root of 4 times omega 1 over RC to the power of 2 plus 4 over LC plus and minus 1 over RC, the whole thing divided by 2. So from this you can calculate your cutoff frequencies now. It's just a simple calculation. Omega c over RC from this divided by 1 over LC minus omega c to the power of 2 is equal to plus and minus 1. And then from that you get 2 different 2nd order equations, and you choose the 2 frequencies from these 2 quadratic equations that give you a positive value, and these are the 2 answers. Okay, thank you for your attention. I hope this has been helpful. Now, to calculate values, you just simply put these numbers in all of these equations that we discussed, and that should take care of the values that you're looking for. Again, this was a band reject as opposed to band pass, or band stop sometimes it's called, because it's passing all the lower frequencies and all the higher frequencies, but it actually stops passing the frequency is right in the middle. Now, intuitively speaking, when you get close to this 1 over LC frequency, the impedance equivalent of this circuit, actually, if you write it, it approaches infinity, at which point this behaves like an open circuit, and therefore this immediately becomes 0. Thank you.